Good evening, all. Am I audible? Hello, am I audible? Hello.
Yes, sir.
Yes, sir.
Okay. Today, as I said earlier, we are going to start a new topic, which is known as principal component analysis, or in short form, it is termed as PCA. Okay. It is principal component analysis. It is a research tool. Okay. Principal component analysis. It's a research tool that is very frequently used by the researchers, and principal component analysis, it has a lot of importance. You will see that though we are today we will be discussing or focusing on principal component analysis, but you will find that there are some software like SPSS, which is quite extensively used for in social science or the management oriented research. There you will see that the principal component there, you won't get any direct option to conduct or carry out principal component analysis. Rather, you will find the option called factor analysis, and under factor analysis you will get different types of options to conduct the factor analysis. There you will get different options like principal component analysis, principal axis factoring. So those kinds of methods you will actually see. So so those methods you will be able to see principal component in case of factor analysis, you will be able to see. Okay, so that's why it is a very useful technique. Okay, just wait. Okay, so now the question is that what is principal component analysis? You can see that principal component analysis is a technique for reducing the dimensionality of data sets, increasing interpretability, but at the same time minimizing information loss. It does so by creating new uncorrelated variables that successively maximize variance. Okay. So basically, using principal component analysis, suppose you have a huge number of variables. Okay. and you have several data. Nowadays, in case of real world data, okay, you will see that in case of real world data, there is a lot of data, huge amount of data you will find. And you will also find huge amount of variables. Okay. So it is difficult to understand if you have a number of variables, okay, or several variables, because the problem is in case of comparison. How can you compare that? Okay, suppose you are comparing some students. Okay, now if suppose there are several subjects or courses, like there is suppose operations research, there is suppose statistics, there is suppose marketing, finance, HR, lot of variables you have. Okay, so if mm, different students, they can score different in different areas or several subjects. Okay, so how can you at a glance, how can you have an idea about your data? Okay, for this reason principal component analysis is used, and it is also in case of it is capable to handle big data. Okay, it is capable to handle big data. So this comes under it also comes under the domain of big data analytics. Okay, so just I'm going to the next slide. Okay, so just have a look at this slide. This PCA plot shows cluster of cell types. This graph was drawn from single cell RNA sequence. There were about 10,000 transcribed genes in each cell. Each dot represents a single cell and its transcription profile. The general idea is that cells with similar transcription should cluster. So what they are saying, that how does transcription from 10,000 genes get compressed to a single dot on a graph? So PCA is a method for compressing a lot of data into something that captures the essence of the original data. So you are able to clustering that data, okay, and you are also able to provide, or you are able to extract something meaningful out of it. Okay, so in this here in this example, they are saying about 10,000 genes. Okay, and you can see that there is along x-axis, this is PC1, principal component 1, and along y-axis it is representing PC2, principal component 2. And you are seeing that all these points, they are actually representing a particular cell in terms of principal component analysis, PC1 and PC2. That means in terms of principal component 1 and principal component 2. Okay, and you are getting some cluster of data. Okay, for suppose for blood cells, for neural cells, okay, for pluripotent cells, for dermal or epidermal cells, you are getting some clusterization of data. You are getting some clusters of data. Okay, so what it is happening here, that using principal component analysis, you are able to group a number of variables. Okay, so that is possible through principal component analysis. So basically, the objective of principal component analysis to or PCA to reduce the amount of data to some meaningful one. Okay, so it can reduce the dimensionality of the data set, increasing the interpretability, but at the same time it can also minimize, it should minimize the information loss. Okay, so this is the general idea of principal component analysis. Now I would like to show you that how it is done. Basically, the mechanism of principal component analysis, it is not required for your research purpose. Just you need to know how to carry out the principal component analysis. Usually people prefer SPSS software over Minitab or other software. So you just need to know that how you can use software to conduct the principal component analysis, and I can also show you that. But still, I will describe the basic of the mechanism that I will tell you, but you don't need to know it. But of course, you should know the interpretation of the data, because if you want to conduct principal component analysis for your research purpose, or even if you want to conduct your factor analysis in your research through principal component analysis, you need to know how to interpret that data. So that I will also tell you. So now let's see that how the things are actually being done. So here you can see that there are 6 mice. Okay, you can see that there are 6 mice, for example. These are your samples. These 6 mice are samples. And for example, gene 1, gene 2, gene 3, gene 4, they are actually your variables. So instead of mouse, you can also take student 1, student 2, student 3, student 4 as your variables, sorry, as your samples. And math, reading, or other type of subjects, or for example, extracurricular activities, these things you can take or you can consider as the variables. Okay, and you have got the scores. Okay, how student one, how much the student 1 has got in math and reading, how much student 2 has got in math and reading, or the sample of mouse 1 for gene 1 is 10, sample for mouse 1 for gene 2 is 6, sample of mouse 2 for gene 1 is 11, a sample of mouse 2 for gene 2 is 4. So in this way, this matrix has been formulated. Okay, so this data, for example, you have collected. Okay, so we are going to talk about how PCA can take 4 or more gene measurements and thus 4 or more dimensions of data. So now just consider, instead of 4 genes, suppose you are having only 2 variables, gene 1 and gene 2. Okay, so if we take 2 variables, then the concept will be easier to understand for principal component analysis. Okay, because we can represent this graphically. So if you plot all this data graphically, if you plot, if you express gene 1 along the x-axis and if you express gene 2 along y-axis, And if you plot all this data, 10, 6, 11, 4, 8, 5, 3, 3, if you plot all this data, then you will be getting like this. Okay, so you can see that it is actually forming some cluster, but it may not form some clusters. From this cluster you can understand that mm, gene mouse 4, 5, 6, they are having gene 1, this characteristics is less, and gene 2, if the characteristics of gene 1 is less, then obviously the characteristics of gene 2 will be also less, and which is applicable to mouse 4, 5 and 6. Okay, and similarly if you have suppose gene 1 expression or gene 1 the characteristics is higher, then obviously there is also tendency that your gene 2 that will be also higher. Okay, so you can also see that here that 1, 2 and 3 these mice are actually representing that, so they are basically forming a cluster. So now we'll move on to the next slide. Okay, so you can see that the average for gene 1 and the average for gene 2, you can easily calculate the average of gene 1 and the average of gene 2. So we can calculate the center of the data. Okay, the intersection point of average of gene 1 and the average of gene 2. So this intersection point you can determine. Okay, so now what you will do, you will move this entire, you will shift this entire set of data in such a way so that the center, it comes to the origin. Okay, so you can understand that the relative position of the data points, they are not getting changed. Okay, so you have done this thing. Okay, so now you are getting this type of thing you are getting. Okay, so now your intention is to find out the best fitted line. Okay, so I have already expressed the concept of the best fitted line. Okay, so suppose this is the any random line you choose. Okay, we start by drawing a random line that goes through the origin. You choose any random line which passes through the origin. Then we rotate the line until it fits the data as well as it can give, given that it has to go through the origin. Okay, ultimately this line fits best. Ultimately you are getting this line that fits the best. Okay, but how can you understand that this is the best fitted line? I have the same way in the regression equation that I told you, that it can try to find the line that maximizes the distances from the projected points to the origin. Okay, the particular line which will have the maximum distances, which can maximize these distances from the projected data points. Okay, so that you are trying to find out that this is actually the largest, ultimately we end up with this line, it has the largest sum of square of distances. Okay, so okay, so suppose you have got now this is the best fitted line. Okay. Now what you will do, this line has a particular slope. Suppose the PC1, it has a slope of 0.25. Okay, suppose this has a slope of 0.25. This means that the data are mostly spread out along, PC1 has a slope of 0.25. It means, or in other words, for every 4 units that we go out along the gene 1 axis, we go up 1 unit along the gene 2 axis. Okay. So it has got a meaning of 0.25 means 25 divided by 100 is equal to 1 by 4. Okay. So for every 4 units that we move along the gene 1, so we will get every 1 unit for the gene 2. Okay. That means that the data are mostly spread out along the gene 1 axis and only a little bit spread out along the gene 2 axis. Okay. One way to think about PC1 is in terms of a cocktail recipe. Okay. To make PC1, mix 4 parts gene 1 with 1 part gene 2. Okay. This is the PC1. Now the ratio of gene 1 to gene 2 tells you that gene 1 is more important when it comes to describing how the data are spread out. And mathematicians call this cocktail recipe a linear combination of gene 1 and gene 2. Okay. So now when you do PCA, the recipe for PC1 is scaled so that this length is equal to 1. Okay. So you have already found out that it is 1 and it is 4. You have found out the slope. So you need to make the hypotenuse is equal to 1. Okay. So if you want to do that, so if you need to divide, you need to find out the hypotenuse, the length of the hypotenuse. If it is 1 and if it is 4, then obviously the length of the hypotenuse, it will become 4.12. Okay. Now if you want to make it as 1, then you divide it by 4.12, so it will come out to be 0.242. Sorry, this will be 1, this will come out to be this side 0.242, and this part, this side will be come out to be 0.97. Okay. So here to make PC1, mix 0.97 parts of gene 1 with 0.242 parts of gene 2. Okay. This 1 unit of long vector consisting of 0.97 parts gene 1 and 0.242 parts of gene 2 is called singular vector or the eigenvector for PC1. Okay. So these distances, the sum of square distances you have calculated. So these sum of square distances, this will be termed as the eigenvalue of PC1. Okay. Also, PCA calls the distances for the best fit line the eigenvalue for PC1. Now, then again you are doing the same thing. You are doing the same thing for PC2. Okay, so in order to calculate this thing, you first you just draw the perpendicular line on PC1, which will represent the PC2 or principal component 2. Here minus parts of gene -1 parts gene 1 and 4 parts of gene 2 you are mixing, and the same thing 0 minus 0.242 parts, because this side is minus 0.242 parts of gene 1 and 0.97 parts of gene 2 you are having for a PC2. Okay, which is also termed as the loading score. Okay, so so you are getting all these things. Okay, so then
Excuse me, sir. The screen is not visible, sir.
yes, I can understand that the net connection, there is some net problem is going on. Now it is visible. Is it visible now? Is it visible? Now hopefully it is visible.
No, sir. Just a blank.
It is blank.
Yes, sir.
Now can you see it?
No, sir.
Okay. Okay, let me try to do something different.